Hello everyone, you're all very welcome to today's webinar where we'll be taking a look at what you have to look forward to in the MasterSeries 2021 major version release coming soon. Joining me today on the webinar is my colleague Niall Burke. My name is Martin O'Gara. I'm a director with Civil and Structural Computer Services, and Niall is one of our lead developers with responsibility for many things, but one of which is all things BIM. So he's going to be taking you through some of the BIM related aspects today. Okay, let's get stuck straight into what we're here today to look at, and that is the new features that are coming in the MasterSeries 2021 version. And one of the major ones is an extension of our Master Key FE Slab Design module to provide facility for fully calculated deflection analysis, taking account of cracking, creep, shrinkage, and load event sequencing. This also extends to the serviceability checks of actual crack control calculations, and that's all done in accordance with Eurocode 2. Furthermore, on that, those analysis results, we will then be looking at how we can assess the deflections that have been checked through the use of check lines, and also looking at then the full calculation of crack widths and looking at those at the service condition. By and large, the technical background to the implementation of this method can be found obviously from the Eurocode itself, but also in further detail. An excellent publication is the Concrete Society TR58, the calculation of deflections for concrete slabs and beams. Excellent publication, and it covers this immensely complex task in quite a bit of detail, looking at all the various variables and attributes and challenges that this problem possesses. It is a very numerically intense engineering problem, and we've worked very hard to provide you with a really optimum and efficient solution in the MasterSeries for dealing with this. Today's webinar, we're going to really try not to get into too much detail on this. This will be a high-level overview of this new feature, and we'll be hoping to follow this up with a more detailed technical webinar in due course, getting into the nitty-gritty technical aspects. Another thing we're really excited about here today, and Niall's going to be taking you through this, is our new link with Revit Structure. We've been able to talk to Revit Structure in the past through the exchange of IFC files. However, we are now doing that directly with Tekla through the Tekla API, which provides a much more robust and fully featured bidirectional link with Tekla structures. And this is the nature of this type of link is something that we have been doing perhaps now for nearly 10 years with Revit Structure, with Autodesk Revit Structure in our mature link that's there. And certainly what we're now providing with Tekla structures is of the same level of feature, and indeed operates in a very similar way. So if you're familiar with the Autodesk Revit link, you'll find the Tekla link to operate in a similar way, and should be quite familiar and reasonable to you to get to grips with. Okay, another really nice new feature that's been on the list for a while, and great to see it realized in MasterSeries 2021, is the inclusion of the design groups for concrete beams, columns, and pads. Really nice feature, allows you to group these entities together so that you can say that that some of their design properties are different from the otherwise global default properties, so you can adjust all sorts of things for these members on a group-by-group basis, as well as providing rationality in the provision of the reinforcement by saying things like all the reinforcement in a beam set is the same for the main rebar or the shear links. For instance, in the case of pad foundations, you can say that you want all the pads in a group to be the same size. And all of that's taken account of and taken care of when we're doing our design, either manually or doing our auto design. We're going to have a look at that. Our Master Key retaining wall module now sees the introduction of highway design to Eurocode. We've had highway design to the British standard for quite a number of years, and the Eurocode equivalent is now available, and that there's various parts of the Eurocodes which cover the highways design. Primarily the loading aspect is the thing that's different, and it comes from BSEN 1991 Part 3, specifically with the UK National Annex, I should say, because it does actually make quite a bit of difference to the loading cases that are produced and are applied. Also in conjunction with that, we have our published document 6694 Part 1 that deals with UK specific recommendations on highway design of retaining walls to Eurocode. So this could be a retaining wall that is part of a bridge abutment, or it could be just a wall that's adjacent to a road surface that has traffic loading. Okay, just a roundup of some other miscellaneous bits and pieces, not something that we'll be looking at in any detail in terms of today's presentation, but just to list them out. Our MasterSeries PartPad Plus license was enhanced for 2021 licensed users to increase the frame analysis and design limits from 100 members to 200 members. So a significant increase there for the PartPad Plus users. Also, you're getting a single finite element surface up to 200 meters squared, and that we see lots of people using that for different applications, but domestic floor slab, something like that, is more than capable of accommodating that. It could be a raft slab that you want to do an analysis on. The MasterKey steel and composite beam design modules, which are two separate entities, also now include for the Weld Design for their plated built-up sections, and there's a few ways in which that can be done. We'll have a look at that. Certainly, through the work that we have done on the slab deflection analysis, considerable optimizations were made for that numerically intensive process, and the overflow of that is that we've seen significant increase in the general master frame analysis. For particularly for larger frames, we've seen speed increases of up to 10-fold through the increased use of parallelism, and also something called multiple solution caching, where we don't throw past solutions in the bin. We keep a number of them and keep reusing them, which is really helping to speed up things up quite considerably. Our MasterKey composite design now implements the full range of Hilti shear connections, shear connectors. So we'll see them and everything about them, and we'll have a quick look at how that's handled. The MasterCAD BIM module also now includes, for the IFC 2x3 version, structural analysis view, model view definition. So we've always obviously been able to accommodate the standard MVD, which is called Coordination View 2, but now the structural analysis view. So if you have a third-party BIM application that is able to export the structural analysis view, which can sometimes be more favorable than, for our purposes at least anyway, than the model coordination view, then we can now import those, and we've seen some examples where that does produce a better outcome for the MasterSeries, which effectively is a structural analysis software. Also, IFC4 support is in there as well for this version. Okay, so we're going to get straight into having a look at this. So the first thing we're going to look at is our long-term cracked section slab deflection analysis. And for this purposes, I'm going to use one of our models here that we use to validate the software. And this is the floor 3 of the BRE Cardington test building, which very conveniently was built under test conditions, which then had the advantage of collecting all sorts of precise data with regards to, for example, concrete strengths at different ages, humidity, accurate humidity calculations or readings and things like that. So we were in an envious position, I suppose, in this type of structure of knowing in detail a lot of the parameters that you may not otherwise know when you're designing something in practice. And to that end, we were able to validate our method against this with all of the properties closely aligned. to show us that we were getting maximum errors of 6% between the measured real-world deflections and those predicted by the MasterSeries software, which is really comforting to know that our implementation of this is correct, and this is just one of our validation models to that end. Of course, the caveat on that is that there are so many variables involved in this type of analyses, and many of which are assumed at the design stage. And any publication that you look into on this, and particularly the TR58 that I referred to earlier, will caveat this detailed analysis with always saying that you've got to expect a range of error in between the model and the otherwise real-world deflections. So that, a range of -15 to +30% isn't unusual, as has been measured. Now, we're not suggesting that we don't have the data to say whether MasterSeries range of error could be of that order of magnitude, but that range has come about from various calculation models and softwares over the years being compared with real-world deflections. So that's just something to bear in mind, and perhaps for you as designers to take cognizance of. So first thing to say here is that this is a model that has already been designed. The reinforcement in it has been specified. We do have some loadings already applied through the finite element surface loading for the purposes of the deflection calculations that we're going to do. So we're going to go straight into the new item here, concrete slab deflections. Great. And you'll be pleased to know actually at this stage the process is reasonably straightforward. We have a slab deflection brief already added. It has already been associated with this slab. So just simply by saying select and pick the slab. So we've only got one slab. So this would associate it with this slab, and also all interconnected slabs as being one connected entity. We're saying that the long-term deflection, or what we would class as the long-term deflection, is in this case this number of days, which quickly translates to 50 years. So that is our long-term deflection that we'll be assessing the deflection at that time. A few other things that are important that you generally perhaps wouldn't think about too much when you're doing standard design, but affect cracking or a creep and shrinkage. Or you do have things like cement type, the Eurocode cement class being specified there. Another thing for shrinkage restraint, which affects your tensile strength capacity. And we'll get into this in a bit more detail, as I say, in subsequent webinars, but these are codified things that are discussed in the codes of practice. And this is something that a bit of background reading will reveal what these things actually do mean. A couple of other things are the allowable crack widths that we're going to check against when we get on to looking at the crack widths. So with those simple things being specified, we're going to have a look at now something we call slab loading events. One of the most important things in relation to this type of analysis is time. And time has several effects. Number one is the variation of material properties over time. So our first event here applies a load at 2 days throughout the duration of the structure, and we've called this strike, which is effectively the load self-weight in load group D1 being applied. So when the slab is struck, the self-weight of the load becomes a load on the slab at the age of 2 days. So the concrete is quite weak at that stage, and this is something then that is obviously taken into account. Also, time has an aspect in relation to creep. So even when you've got constant stress in a structure, the deflection of the structure will increase over time due to the creep nature of the structure. So the creep strains will increase with the passage of time, even under constant stress. So going through this, we've got a few other events. We've got a construction load occurring at the same time that the slab is struck and ending at 28 days. That's already been applied as an FE surface load in load group L2. We've also then got a few other events which are quite interesting, and this is the construction load from the slab above. So another slab above this is being cast at 12 days, and the propping action from that is then being transferred as a load through an FE surface load in load group L3, and for a period of 2 days. We've then got subsequently another slab above that yet again, so we've got propping through 2 levels, and there are publications that talk about how you calculate that propping load through, and generally, obviously, as subsequent slabs get applied, so you might even have another slab above this yet again, those loads would generally decrease. But those were documented for this Cardington structure, and they've been applied in load groups L3 and L4 as finite element surface loads also. Final load then is a load applied at 56 days, which we're saying conceptually is our partition loads throughout the duration of the structure in load group L1. And because this is our looking at the factors here for the quasi-permanent load case, all of the other items have a factor of 1. This has a factor of 0.3 as its psi factor for the quasi-permanent condition. Final thing here is the beta factor, which is a factor in the Eurocode that takes into account the duration of the load. So if you've got some loads that are quite transient and short term, then they might have a factor. They would have a factor of 1, whereas long-term loads would have a factor of 0.5. I might argue that this variable part of our partitions might have a factor of 0.5 as well. If you want to include the frequent load case, you can do that, and you might say that the frequent load actually perhaps is the short-term one and has a beta factor of 1. You do then have to choose which of your load groups is the frequent load and include the frequent load as an event with a start and end time also for that frequent load case to be considered. We're just going to stick to the quasi-permanent load case for what we have here. Great. So with those events now specified, one more thing. In the events, you can obviously add in new events just by typing in a row or delete an event. There's add new event here, deleted event also. But you can also save those events to a file and re-import them from a file to speed things up for subsequent models that you might want to look at. Okay, now we've got another specification here for the humidity and ambient air temperature. So we're saying we have a relative humidity here of 50% throughout the 50 years of the structure and the ambient air temperature of 20 degrees. Those are our two defaults. If you do want to vary both of those over time, you can enter in extra rows and create a profile of those, and the analysis will take those into consideration. Indeed, Eurocode has a method of taking variable temperature into account in its calculation of the creep coefficient. So those are the extents of our inputs, and we're actually now ready to go ahead and do an analysis. And in fact, an analysis already exists on this, but I'm going to push the button again to do it, to show you the performance that you can expect, obviously in this case dealing with a single slab. So the analysis is extremely intense in that with each time event, the cracked nature of each element in the slab needs to be assessed. That has the effect of redistributing load, producing more cracks. Also the creep coefficient, the compound creep coefficient at each step in time is calculated for each of the elements. That analysis is just completed in just under 20 seconds there, and it has done all of the nonlinear calculations. So with each time step, the nonlinear calculation is done until we get a converged solution, both in terms of deflections and crack stability. With the analysis complete, we can start to look at some of the results. One of the things you might want to look at first of all is some of the contour outputs. So you can see the contour deflections for the different days. So this is the 2 days when the slab is struck, getting the deflection profile there. And we can walk through the other days of 12 days and 14 days at the end of the application of the slab above, before the load is removed. So you can actually see there a little bit, if maybe we come forward to the 26 days where we've got a maximum deflection of 22.7. Obviously at the end of that load duration at 28 days, the load is the same. However, you're getting a little bit of extra deflection due to the presence of creep, even though the load is the same. Our partition loads then get applied at 56 days, and again, with that load being applied with no change in load, we're getting about a 4 millimeter increase in deflection between those 2 points in time, and that would be entirely due to the creep. The creep factors that are involved at each of the time steps can be looked at. Very little creep occurring at 2 days, I would imagine, but then you're getting a little bit of creep then coming in at 12 days, and this is the actual Eurocode creep factor that you have here. And if we step through that, interestingly, at 56 days, you get a distribution of creep coefficients that you might not expect, and that's because the partition loads are actually only applied on the inner 2 bays as a finite element patch load. So that variability produces this pattern, because remember what we're looking at this point in time is a compound creep due to the fact that we've got, at this point in time, we've got loads that have been applied at different stages in time. So each of those components of load that have been applied at different start positions and end positions have an effect of a component of creep, and the Eurocode has a methodology of developing a compound creep value for taking into account all of those different loading events up until this time here of 56 days. But of course, as the passage of time increases those load events, we're up at 50 years now, so the variability of the creep starts to level out, and because we get more of the creep then being influenced by the long-term aspect of the load. So the long-term creep there having a maximum of about 2.7 as a factor. A few other things that are really interesting are then the crack ratios. This is what the Eurocode would class as a load distribution factor, which is really just a measure of how much the slab has cracked. So values approaching 1 would indicate a very extensive crack, whereas values of 0 indicate no cracking at all. So we have here the little grey lines indicating the crack directions, and I'll just zoom in so hopefully you can see that clearly on your side. Cracks obviously occur not just in one direction but 2 directions, and we have the other direction, or the related direction here. Those are resolved into the principal directions of forces, and the cracking itself then is calculated in those 2 perpendicular principal axes, and the directions of those given to you there. So yeah, that's quite interesting just to see the extent of the cracking. Another really interesting thing is the time of the cracking. I should say actually those crack extents are the maximum crack ratios that have occurred over the full time period of this analysis. Obviously, the crack will occur due to the presence of load. More load might get applied and the crack might increase. So these values would change over the analysis of time, but their maximum values are recorded here. Also, once a crack occurs, it can't disappear, it can't go away. Its extent is also retained. So once a crack has developed of a certain value, it would be maintained at that value until it actually increases. We also then have the time at which the first crack occurred, and we can see that we've got most of the cracks occurring here at a time of 2 days. In fact, all of the cracks occurring at a time of 2 days. And so that's really the time that the slab is struck, which is no great surprise, because at 2 days we can expect this concrete to have very little strength, tensile strength, and none. Even though more load is applied at other subsequent times, the first cracking didn't then was always at the time of 2 days, and that's true for both directions. Okay, so we've got those values, but those values in themselves don't actually allow us then to produce an actual check. For a check, we must then look at a part of the slab and do something called a check line. So we have a few check lines in place here. I'll just turn off this. So with this check line, we basically just have a line that's drawn in from one support point to another in this case. And the check line then is able to extract from those deflection calculations the deflection values and check it according to check criteria. So the criteria is specified basically in this part of the software, and the criteria can be saved in a set, and the set basically contains a collection of criteria that you can apply. So we've created some here. One is the long-term deflection at 50 years. It is relative to the ends, which means the support settlements are taken into account, and it's checking at a deflection of span over 250. We've also got then a second one we've called a partition deflection check, which checks for a differential deflection, which is key, and the difference in the deflection between the 56 days and the 50 years relative to ends at span over 360, and that is simply then what we see coming out here. Just going back to that, a few other things. A check set can be set up to be like a cantilever deflection check, so that it does look at that pattern instead of the deflection between two ends. You can also do things like export these deflection sets to a file and import them to make the sharing of them a little easier. So perhaps we might want to create a new check line. So we can navigate between check lines just simply by clicking on them. These two have already been created. If we want to create another one, we can simply just say add, and let's just spin this around a little bit, and we're going to draw that third check line in between this point and this point, and then just make sure it's got some criteria set, and now we're getting the results there on that. So that's the extent of your deflection checks done. So we'll move on from this now and have a look at the calculation of the crack widths. Now, I suppose you might think that those are related in some sense, but the calculation of the actual serviceability crack widths are somewhat independent from the calculation of the deflection, even though it includes cracked sections. The calculation of the crack widths in accordance with the Eurocode is done here. So we're looking at the maximum point of cracking in the top of the slab and the maximum point of cracking in the bottom of the slab. And we can see we've got a little problem here with regards to the top of not being above the 0.3 that we've specified. But we can see the involved calculation here. It is recognizing that the principal direction of forces is outside the code tolerance of 15 degrees. We must look at this in its principal axes and not the reinforcement axes. And taking into account the axial force in the moment, we've got a calculated crack width here of 0.546 millimeters. So we do have a failing issue there, but we can look at the crack widths in a contour format. Now this actually is giving me the actual crack width in two principal directions also. But more interestingly is the crack unity, which basically draws a contour, a unity-based contour where anything that's blue and green is passing, anything that's orangey red is failing, and you can see very little of that. And if we examine the two directions, we can see little bits and pieces of indications of failures at the column faces. So that, you can see that even though that's giving us a failure problem, it is actually really very localized to the column faces. Countenance is taken here of strip averaging to an extent because we do limit the service stress of the rebar to what would be the acceptable or the maximum service stress based on. So even though we're getting a service stress here of 705, it is actually limited to this value because we know the actual ratio of the quasi-permanent load to the ultimate loading case condition, and taking into account the reinforcement factor of safety, we know that in reality, due to design strip averaging, that service stress indeed would be much smaller than that. So that's even taking that into account, we're still getting a slight problem, but very localized problem there with regards to that. Okay. So at this point, we're going to come away from this, and I'm going to let Niall take over and show you what we have to offer with our Techless Structures link.
Hello everyone, my name is Burke and I'm one of the software developers at MasterSeries. One of my main areas of work is concerned with Bim development, and so today I just want to take you through our latest offering with regards to Bim, which is a Tackler link. For anybody who's used the Revit link in the past, it follows a very similar process. So as you can see here, I've just got a basic model, 3 materials, concrete, steel and timber. The steel has a variety of profiles applied, from CHSs to UBs, SHSs, twin PFCs, and at the back we've also got some angles for bracing. Some of our members are also decorated with web openings, so as you can see here we've got a series of circular openings and a rectangular opening in the middle. For a rotator view, you'll be able to see a slab, which is an opening for a staircase. We've also got a wall with a cutout here for a doorway. So we want to bundle up all these features of the model into an export file that can then be interpreted by MasterSeries. And to do that, we just need to go to our applications and components, search for MasterSeries, and from there we can open up the link plugin. At this point you've got 2 options. You can create a bidirectional link or a unidirectional link. A unidirectional link is useful for when you just want to take your Tekla model and pass it to MasterSeries and continue working with it in MasterSeries only. However, if you want to make changes to that MasterSeries model and bring those changes back into Tekla, then you'll need to create a bidirectional link. And that's what we're going to do today because it's a more involved process. To do that, all we have to do is create a new link, browse to the directory that you want to store the link in, and give it a name. At this point we've created a link, so let's have a look at that directory. Okay, so you can see here that we have a Tekla MasterSeries link folder, and within it we have an actual link file. This link file here is the overriding file that controls the mapping between Tekla and MasterSeries. We also have 2 folders here, MS and TK, one for MasterSeries and Tekla. And in here you'll be able to find your exports. Now at the minute there aren't any exports because we haven't submitted our actual model to the link. So let's go ahead and do that now. Okay, now we have our first export from Tekla. At this point we can go ahead and connect to the model from MasterSeries. So with MasterSeries open, you just need to go to Import, Tekla link, browse to your link file, which is just this MSTK file. Now by default it'll apply a MasterSeries file name that's the same as the links, but you can rename that to whatever you want. I'm just going to call mine MasterSeries model. Okay, so if I switch on 3D view, you can see that it's taken through the 3 different materials, concrete, steel and timber. And our steel sections have all the profiles that we expect to be applied from our CHSs, the UBs, the SHS, the twin PFC, and down the back we've also got our angles. You can also see that the members that have been decorated with the web openings have their circular openings and the rectangular opening, and that the FE slab has come through with the opening in it for the staircase. Now at this point you've got 3 options. You generally want to carry out a create, a modify or delete. So let's go ahead and carry out each of those in turn. So the first thing I'm going to do is delete one of the members. I'm just going to get rid of this column here. Next I'm going to change one of the column sections. Let's change that to RHS. The last thing I want to do is create a new member. I'm just going to insert it here. Now at this point we want to open up the link again, so all we have to do is go to Bim Exchange Tackler, and as you can see the UI is pretty much identical to that in Tackler. And you also have some information here about your link file and the status of the link. As you can see, we haven't actually carried out any exports from MasterSeries, and none of those exports have been imported to Tekla. So let's go ahead and do that now by clicking Submit Changes. At this point, if we go to our Tekla link directory, we'll find that the MS folder now has 1 export. So back in Tekla, if I open up the link plugin, you'll see I have an update pending. When I click on that, it brings up a list of the changes in the model. So you can see here, we've got a member to be created. Member 2 has had its section changed, and another member is to be deleted. If I click on these items, it'll highlight the member in question. If I changed any of my grid lines, I'd also have a tab up here, specifically for grid line changes, but because we didn't change them, it's been removed. You can also order your changes according to the type of change. So you can see here, we can list the changes according to the section, the angle, the ends, the members to be created and the members to be deleted. So I'm happy with all these changes, so I'm going to import them all. So as you can see, our CHS column has been deleted. The other CHS is changed to an RHS, and we've inserted a beam here. Alright, so far we have created a link from Tackler, exported the model, imported that model into MasterSeries, made changes, and applied those changes in the Tackler model. Now, you could have started that model from Tackler or MasterSeries. It doesn't matter. You just go through the same process. And that kind of covers all the main operations of the Tackler link. The only other things left to discuss are a few limitations and the Tackler side settings. So you can create FE slabs in Tackler and MasterSeries, and you can export them, and they'll be imported the first time around. But any changes you make to those slabs will not be brought back to the original model. They're unidirectional. And I'm hoping to work with Tackler in order to make those bidirectional, but for now it's unidirectional only. And the Tackler side settings, if you go into your link plugin, you'll see there's a settings button down here that isn't available from the MasterSeries side. So I click that. If we have sections in MasterSeries, T sections and I sections that aren't recognized in Tackler, you can choose to import them as built-up sections. Now, the one thing to bear in mind is if you're using a bidirectional link, when that model comes back to MasterSeries, it'll change that section from an I section or T section to a built-up section. I would recommend you use it for unidirectional links only. And the other item here is default classes. So you can apply a class to your 4 different materials, I suppose, your steel, concrete, and timber. And by default, they just map to a very similar color to MasterSeries, but you can put whatever you want in there. And so that kind of covers everything in the Tackler link. And all that's left to say is that it's an ongoing project, and I look forward to hearing your comments and suggestions going forward. Thanks for your time.
Thank you very much, Niall, for that. Hopefully you can all hear me again and back on my screen. So we're going to proceed now and come back to MasterFrame and have a look at our concrete design groups that we mentioned on our initial presentation. So a nice little interesting model here, steel composite superstructure with a concrete substructure below. At this stage, we have the new option to access our concrete member design groups at the MasterFrame stage. So quite similar to other types of design groups that you may already be accustomed to, such as the composite steel, the concrete now sits in the same place. So we have a group here already set up for beams. In fact, we've got a few groups set up for beams. But conceptually, just to see what this does in the first instance, those of you who have been accustomed to doing concrete design through MasterSeries in the past would know that when you get into the concrete design, you're presented with a whole host of what we called basic data and defaults. So those were defaults from anything to do with concrete grade to concrete cover to detailing styles to auto design parameters. And those were a singular set for the entire structure. The groups basically allow you to vary those parameters on a group by group basis. So effectively here, those basic data and defaults, you can see what they are at this stage and access them in this format. Now this is a reworking effectively of the previous concrete basic data and defaults that you would have been familiar with into this more of a property grid style format. So this is the new style of global basic data and defaults going forward. So you've got global things that don't change between groups. Things like drawing settings and things like that you know that are common. Common actually means stuff that can be changed on a group by group basis, but is common for each of the sets in terms of a global. So things like you know what your common reinforcement is for all of the different areas, common auto design properties and things like that. And then you've got the specific settings for beams, columns, and pad foundations. So those are, again, things that you would have been accustomed to previously. Covers that supports your auto design parameters for what they are, and all of those have been rationalized. And the nice thing, obviously, as well, is you get you know a detailed explanation for each of those and what they actually do. Hopefully things will be just as easy to find there as they were previously. Those defaults also can be saved. So if you make changes to a default set, you can say, I want this to be the new defaults going forward, or revert to the standard out-of-the-box MasterSeries defaults, or you can save them to a file and load them again from a file. Okay, so but those can be changed on a group by group basis, as I've said. So this group effectively selects all these beams at the front, and it's made a few changes here. It's changed some of the detailing settings in that. What we can see here is that for each category, you have an option to say you want to overwrite. So on a category by category basis, you can say, well, I want something different from the global. I want my own local values. So the detailing here has been chosen to be overridden by local values. So we've said things like that we want to bring the top and bottom bars to midspan bars to the supports. So that's different from what we've specified in the global basic data and defaults. Another thing that we've said for this group, which is optional, is we said we want all the bars in each of these 5 beams at the front here to be the same main bars and same shear links. Now that presents a bit of a challenge in that we have in this symmetrical arrangement here, there's varying lengths, so obviously that is unachievable where you've got different lengths of beams that can't have the same reinforcement, the same bar lengths. So the program will group these outer 2 beams, for example, into their own little subgroup. So it does have a tolerance length whereby it will try and group together members of similar lengths to provide the same values of reinforcement. Moving on to our second beam group, that's quite similar. This little control here allows you to do things like expand all if you want to see quickly what items have been overridden and which haven't. So the only thing that's been done here is to say, yeah, the reinforcement's the same, but all the parameters are the same as per the global settings. For the columns, again, I'm going to say expand all here. We've got these columns at the front, and they have specified the concrete grade to be something else, C50, C40, 50, or C50 concrete along the front there with no other settings changed. I think we've got another group of columns then which again say that the main bars are the same and then have some reinforcement overrides as well. So on a similar basis, we've got a few pad groups. So this is our pad foundation design group, and let's just expand all there on that. And yeah, the only thing that's changed here is that the safe working pressure has been overridden for this group over what has been specified in the defaults. And we've got another group here which has some reinforcement overrides and saying that the detailing style is U-bars, whereas I know the global default is straight bars. So we'll have a look at how those groups then feed into the design and what they allow us to do. So let's head on over to the actual concrete design. Great. So let's have a look at the first beam here. As we've said, it highlights all the members to show you that they're in a group, but the ones then that are the same reinforcement are shown together in their 3D profile. You also have a quick access to the group settings from here, so you can visit the groups, change settings in the group. So this is the current group, or you can actually create more new groups on the fly without having to go back to master frame, as well as change the settings of the group. Without even having to go there, you can actually also say with these quick set buttons that you want the reinforcement to be the same and the shear links to be the same, or turn those settings off as you would see fit. So we've got those 2 inner beams being the same, and the middle one a length of its own. Just looking at how this performs actually, what happens when members are of the same group, you get a superimposed bending moment ultimate envelope. Likewise, if you told that the links are going to be the same, the link force is superimposed ultimate envelope for all of the items that are deemed to be the same reinforcement. So that allows you, when you're designing, that you know you're providing reinforcement that's going to suit the whole group. Likewise, if I change any of my reinforcement, so if I just do a quick change there from a 16 diameter bar to a 12 millimeter diameter bar, have a look at the other one, we can see that that's came about there as well. Again, if I click and drag any one of these here and change the curtailment, that curtailment pattern is going to map across as well to that. So we can see actually the other localized parameter settings coming in, and that it's taken the top and bottom bars to supports, whereas if we look at another member that's not part of a design group, that those middle span bars aren't taken to supports. In inner group, all the lengths are the same, so these are all being specified with the same reinforcement, both shear links and main rebars. The columns, again, these ones aren't all the same reinforcement, but they are all the same parameters, so anything that I would change there in terms of the parameters would apply to all of the columns in the group. The inner columns here are all the same reinforcement, so again, likewise, if I were to change the corner diameter here from 16 to 12s to 16s, you'll see that applying across the group as well. Moving on to our pad foundations, I'm just going to actually quickly say that the pads in this group I want all to be the same size and they're all highlighted together on that basis. And if I were to turn around and say, well, actually I want to change the pad foundation size, we can see that that change applies to all of those. The same thing will happen if any changes that are made to reinforcement. Pad group at the back here, the only thing that was changed with it, I should also say this pad group I think had a safe working pressure of 200 kilonewtons per meter squared, which you can see, and the pad group at the back had a different detailing style, had a U-bar detailing style as opposed to a straight bar detailing style. So with a bit of imagination, you can see how those groups will be extremely useful for you to vary really any of the design parameters throughout your structure for different purposes, and hopefully you'll find that extremely useful. Okay, so coming away from that, we're going to now move on to having a look at our retaining wall module and the highway design. Before we get looking into the highway design, there's a really nice new feature here which we implemented to facilitate the highway design, and that's in the soil data. You now can, previously you had to specify your bearing resistance, your ultimate bearing resistance capacity. In Eurocode, you always deal with two different soil states. It's referred to in the UK design approach 1. You consider two positions of one where your soil is factored and your loads aren't, and then or loads are less factored, and then you consider the position where your soil is unfactored but your loads are factored. So the M1 and M2 soil factors produce different bearing capacities, and you could have input both of those there to specify what the two different bearing capacities were for the two different Eurocode retaining wall combination 1 and 2 capacities. But that capacity can now be calculated in accordance with Annex D of the Eurocode. So you get your full bearing ultimate bearing capacity pressure, allowable pressure being calculated from that. Now, it's a bit of a confusing area, this, because there's very much a distinction between the ultimate bearing capacity and then the serviceability permissible bearing capacity. The ultimate bearing capacity is the capacity at which the soil will fail. It doesn't limit deflection or anything like that, which is another area of concern. So with this ultimate bearing capacity, the thing to bear in mind is that lots of things affect the ultimate bearing capacity, and one of which is the actual size of the foundation. So in this wall, it may, obviously we're designing retaining walls per meter run, but the actual size of the foundation in terms of its length may have an influence if it's relatively short relative to the 5 meter width here that I have. So if the retaining wall length was say 11 meters, it would be best to provide that, and that may have a slight impact on the bearing resistance calculation. The bearing resistance also is determined by the inclination of the loading that comes down, so the angle of the horizontal and vertical loads that come down and the angle that makes. So you do end up getting quite a variability of ultimate bearing capacity, even through different loading cases, as well as the fact that different loading cases have different material factors. So that really has the result of, we'll have a look at all the different bearing capacities when we start looking at the highway design itself. So you can look at the drained and undrained bearing capacity there. Now, I mentioned previously there that this was the ultimate bearing capacity. What happens at service? Well, at service, you want to ensure that you don't have excess settlement, and that is typically done through the use of factoring the ultimate bearing pressure capacity, and typically a factor of 3 is used. So we also now check the serviceability load case condition for Eurocode, and we will take the calculated ultimate bearing capacity or the provided ultimate bearing capacity values with a factor of 3 to ensure that your serviceability bearing pressures are within a factor of 3 to ensure that excess settlement hasn't occurred. Another new thing that we have in the 2021 version is checking for the wall stem L/D. Now, this is something we've included from the request of many users. I guess in the past we've had a bit of reluctance to do that because obviously L/D checks we associate with a check against deflection. And whilst the L/D check is useful as a check on the local span deflection, it doesn't take any cognizance of the overall wall movement. It's a check on the performance of the span relative to the movement of the base. So we do have a little caveat in the design output once we get all the way down to it. When the L/D checking is included, that it is relative to the wall span and doesn't take account of the overall wall movement, which is a soil structure interaction thing and obviously much more complex and not included in the software. So now looking into the highway design aspect itself and speeding things up, trying to make sure we get in under an hour here. The highway design to Eurocode is more complex in the British code because obviously you've got the same concept of highway loading. The British code had HA and HB loading. The Eurocode has something equivalent to that called load model 1 and load model 3 loading. So you do then have the, if this were a bridge deck or a bridge abutment, which I've specified here that it is, a lot of different scenarios of where you've got loading on the deck but not on the retained soil, traffic loading on the soil but not on the deck, but also then you've got a number of different combinations of GR combinations that the British code defines in EN 1991 Part 2. There's a whole host of combinations. So when you consider the combinations that you need for deck and soil side loading, as well as those that are in the Eurocode, and then couple that with the fact that you have the need to do a combination 1 load, a combination 2 load, and a serviceability load for each of those sets of load combinations, we end up here with a table with 21 loading cases of 7 subsets with 3 loading cases per pattern of load, I guess you could say. So those have all been filled out with the default load factors, combined load factors, for frequent and cases, and combining with appropriate psi factors for a number of different permutations. Now the default titles of those permutations is given here, so you can see the title of those sets 1 to 7 and effectively how we have set them up to be. But you could effectively use these 7 sets in any way that you see fit. However, the default values that we have specified here are what we feel is appropriate in accordance with the code. If you do change any of those and you want to reset them back, there's a reset button here which takes everything back to our default values. For the bridge abutment loading here, we've got some LM1 and LM3 deck loads applied to the top of the wall. In addition to that, we've also got the vehicle surcharge load on the retained side. There's a loading model for that in PD 6694, our published document to complement our UK National Annex of the highway design. And it replaces load model 1 and 3 with normal vehicle loading and special vehicle loading and special order vehicle loading. So there are different ways in which it applies a point load at the top of the wall and a uniformly distributed load in the back of the wall to accommodate that type of vehicle surcharge loading. It is actually quite a bit more onerous than the equivalent British version, and can end up producing these are the bending moment diagrams, and these values over here are the ones that are come about due to the vehicle surcharge loading, whereas the lower values here are more the construction stage. So you can see the amount of impact that that vehicle loading is having on this wall. So coming down through the code, we can see the surcharge loading listed out here in terms of the values that are being applied. But then we can see all of the different combinations of loading that have been described here with the titles and the factors that have been defined. And then all the checks on the sliding, the overturning and sliding, and also then the bearing checks on each of those. And you can see the bearing capacity that's been calculated for combination 1, combination 2. So you can see quite a difference there between the factored soil and the unfactored soil, and the difference that makes. And then you can see the factor of 3 coming in on the safety factor of 3 coming in on the service case to ensure that no inappropriate settlement is taking place on the wall, and that repeats itself throughout all of those different cases, both for a virtual backloading and a wall backloading. And then that obviously feeds through to the actual design of the wall stem itself, the model design factor that is recommended, which basically augments or multiplies the design forces by a factor of 1.2 at design stage. Also, just like the British Code, the at-rest earth pressure is included here, with the effective 1/over consolidation ratio coming into play there as well. And all of those design calculations then are listed out in a summarized fashion for the critical loading cases for both the wall stem and the wall base. Great. Rushing through that quite a bit there at the end. Just about time to have a quick look at our composite beam program and the inclusion of the healthy shear studs, which is really just a quick glance, to be quite honest. We have a model here, and the healthy shear studs are where you would expect to find them, along with our other headed stud connectors and built into the software. And effectively their capacity, their effect that they have on the in combination with the decking, with the deck modification factors, the K factors are all automatically calculated, along with all the geometry checks that are done. If you're interested in finding out a little bit more about those, you can head on over to the Hilti website and download the Hilti XHVB datasheet for the Hilti shear studs. That's what they look like. They're shot fired straight through the metal onto the flange of the beam. They can be positioned both parallel with the beam and perpendicular to the beam, and all the different K factors vary with that, as well as a host of geometrical rules with regards to clearances and required trough widths. All of those checks are included in the software and are being checked. So for instance, if we were to say, we've got maybe 3 per trough, and we then maybe looked at reducing the width of the flange down, then we're saying, okay, no, you can't have a flange that narrow because you can't fit in your 3 studs together, whilst including the spacing required of those studs and the width of the stud itself. So that's all great. Did mention as well, while we're here, that this is a built-up section, a plated section. We are now including for the Weld Design, which is available in your 2020 version if you are a maintained customer. But the Weld Design is accessed through here. We can see the weld output being given in the software for the ultimate condition. The default really is that this would be set to auto, which means the program is going to look and see, okay, what size of weld is required, but then obviously sensibly it says it's going to provide you with a minimum of a 6mm fillet weld. If you then wanted to optimize that a little bit, you can say, well, I'm actually going to specify a 6mm fillet weld, and when you specify the weld size, you get the option of saying it has some partial penetration if you need a little bit more. But you can also then do a hit and miss. So you can say, I want a hit and miss unit length of, say, 250mm, and the program then works out for every 250mm you need 39mm of weld, which seems quite low, obviously, when originally only a 1mm weld was required in any case. So that's where you find that, and the same thing is done on the standard steel design for built-up sections. You find it in exactly the same place in the section property definition area. Okay, that brings us to a conclusion of our presentation. So it just remains for me to say, really and truthfully, thank you very much for your time and attendance here today. You will be getting a recording of this webinar, and we hope to release MasterSeries 2021 to you in the next number of weeks, certainly before the end of June, We're in the processes of finalizing our testing and version checking. So we really hope you enjoy using it, and we look forward to seeing you at the next webinar.